Hello, let's recover the important results of the relationship between energy, momentum, and mass. E squared is equal to m squared c to the fourth plus c squared p squared. This is a general equation valid for all particles. It relates the total energy with the momentum of the particle and the rest energy mc squared. But if the particle has no mass, like the photon, then the equation reduces to E equal to Cp. We are going to use this result to apply to an elastic collision between a photon and an electron, into what is known as the Compton Effect. Albert Einstein showed that light is made up of particles, photons, and when individual photons interact with individual particles like one electron, we need to consider them as that. They interact through elastic collisions where photons have a total energy of Cp. We also know from the work of Max Planck that the energy of a single photon is frequency nu times h, where h is Planck's constant and nu is the frequency. But we also know from the work of Louis de Broglie that the momentum is related to wavelength through lambda equal to h over p. Putting these three equations together, we obtain that the speed of light c is equal to lambda times nu, wavelength times frequency. This is the equation that we use to measure the speed of light through the scientific chocolate chips. Now, let's consider a photon that impacts with an electron in a metal. The photon collides with the electron and leaves deflected. We are going to assume that the electron is initially at rest, and we are going to study the effect of the collision on the photon. This work was done by Arthur Compton in 1922. Because in a collision there is going to be momentum and energy transfer, the photon after the collision will have a different energy as that before the collision. The speed of the photon won't change. Then the change in energy will be in the frequency. So the incoming photon will have frequency nu and the outgoing photon will have frequency nu prime. The photon will leave in an angle theta with respect to the incoming direction. On each side, the electron will recoil also with certain angle related to theta. We can make a scheme of this. Here h nu over c is the initial momentum of the photon, h nu prime over c is the final momentum of the photon, and p is the momentum of the recoiling electron. In this collision, energy and momentum have to be conserved. Because of conservation of momentum, these three vectors make a triangle. Using the theorem of the cosine here that says that the square of one side is equal to the sum of the squares of the other two sides minus twice the product of those sides times the cosine of the angle between them. We apply this theorem here and we get Now, let's apply conservation of energy, where initially we have the electron at rest, which I will square both sides and rearrange. Here, remember, the initial energy of the photon is h nu and the final energy of the photon is h nu prime. The initial energy of the electron is mc squared and the final energy of the electron is E. And the final momentum of the electron is P. I multiply by c squared the equation of the momentum and subtract from the equation of the energy. I do a little of wibbly wobbly timey math stuff. I use the relativistic energy of the electron, E squared minus C squared P squared, equal to m squared C to the fourth, and after a bit more of wibbly-wobbly math, I get because C is equals to lambda times nu, then the change in wavelength is equal to h over mc, which is called the Compton wavelength, times 1 minus the cosine of theta. So, depending on the scattering angle, the wavelength of the photon is different. This is something we can measure in the laboratory and put our detectors at different angles and detect light of different wavelengths. And this is explained by using both quantum mechanics and special relativity. The maximum change in wavelength happens for the photons that recoil completely, so that theta is 180 degrees. If there is no scattering, theta is 0 and wavelength does not change. Compton scattering has applications in radiobiology and radiation therapy. It also appears in some astronomic phenomena, like in the interaction of matter and radiation near the black holes, and it's used to detect some galaxy clusters.